And this is Mechanics Homework Booklet question 45, and we're given information about a student adding a series of masses to a vertical metal wire, circular cross section, and measures the extension. So we get a force extension curve. The figure below is the force extension graph of the data. First of all, mark on the figure point P, the limit beyond which Hooke's law is no longer obeyed. So I'm trying to mark P here at the end of the straight line section of their original line. Outline how you could use these results and other measurements to determine the Young modulus of the wire. Well, if I say the Young modulus is FL over A delta L, I outline that in question 44. So the force is Young modulus times A upon L times delta L. So the gradient would be the Young's modulus. Gradient is equal to Young modulus times A upon L. So the Young modulus is the gradient times L, multiplying both sides by L divided by A. Young's modulus is the gradient times L upon A. So that's how I'd get it. So what are the measurements I'm going to need? I've got the additional measurements I'm going to need. I'm going to need the original length and the diameter, from which I'm going to calculate the cross-sectional area. And I'm also going to need to calculate, to use that, I'm going to need to calculate the gradient of the linear section of the wire. So those are the three marking points there. When the wire is extended to A, the masses are removed one by one and the extension remeasured. Draw on figure above the shape of the graph the student will obtain. So what we're looking for here is a line which is parallel to the original straight line section and drops back down to zero force, but leaving me at that point an extension. We've had some plastic deformation, so it's crucial we end up with some extension there. So the marks are the mark is for a single line from A, parallel to the straight section of the original and ending at the horizontal axis. Explain why the graph is the shape you have drawn. Two marks here, simply one for saying the plastic deformation. We've got plastic deformation, so we do not end up back at zero extension, and the idea of the gradient matching, because it's for staying bonds in the metal that's been stretched, unstretched. There's just been a realignment in between, so we're going to have the same gradient for that reason. The metal in the wire we studied is used to make a cable 6mm diameter, and the Young's modulus is 2 times 10 to 11 pascals. We've got to calculate the force to get a 0.2% strain. So a 2% strain means the strain is 0.2 over 100. It's 2 times 10 to the minus 3. Why is it that? Well, if I want to go from a strain, which is just a fraction, to a percentage, to go from a fraction to a percentage, you multiply by 100. So to go from a percentage to a fraction, I'm going to need to divide. So I've got a strain of 2 times 10 to the minus 3. I'm also going to do a little side calculation of the area. Area is pi times half that diameter, 3 times 10 to the minus 3 squared. That gives me that area. The stress, because Young modulus is stress over strain, the stress will be the Young modulus times strain. There's the Young modulus. There's the strain we worked above, giving us that value of stress. And the force will be the stress times the area, because stress is force divided by area. So it's going to be that stress we've worked out multiplied by the area I worked out over here, 11.31 kilonewtons. So the marks there, 1 mark for calculating the strain, 1 mark for successfully calculating the stress, and there's the answer mark. Again, not specifically asking about significant figures, so no problems with additional significant figures. In F, we said this cable is used to lift a mass of 600 newtons, and we're asked to determine the maximum acceleration with which the mass can be lifted if the strain in the cable is not to exceed that 0.2%. So we've worked out the tension that will give us that 0.2%, so that's what we're going to work with. We've got a lift, I've got tension upwards in this case, I've got weight downwards, they're in opposite directions, so the net force upwards is T minus W, is MA. There's the tension I worked out previously. There's the weight, mg, equals ma. And I can work that through and I get an acceleration of 9. So the marks there are for dealing with the tension and the weight, gets you a mark. We've got the force has to the force has to be less than the difference between the two, and the acceleration therefore is less than that divided by the mass, getting us out to that third mark there. An engineer redesigns a crane to lift 1,200 kilogram load at the same maximum acceleration. Discuss the changes that should be made to the cable of the crane to achieve this without exceeding the 0.2%. So, because from the equation I wrote down above, I can write T is W plus MA. Okay, so that's that equation there. I can rewrite that as T, the tension, is MA plus mg. Now, same mass in both cases, so if I double M, I've got to double the tension. So if I'm doubling the tension and sticking to the same strain, I've got to stick to the same stress. Therefore, I've got to double the cross-sectional area. So I've got to double the cross-sectional area. That's, of course, same as increasing the diameter by square root of 2 to keep at the same stress. The alternative to that is I could have a wire with double the Young modulus to get the same strain for this increased stress. So first mark for pointing out that I need twice the force. I'm not quite sure how this came to 3 on the mark scheme, it doesn't, but yeah, okay, there are two, and then a mark for each of the two possible ways of keeping the strain the same, either by having the same stress by doubling the area, or by having a Young modulus with double this Young modulus, having a wire with double the Young modulus. So that's the mechanics homework booklet, question 45.